Chapter 2, Exercise 2.99, Part A. A laser produces 23.6 milliwatt of red light. In 25 minutes, the laser emits 1.15 times 10 to the power of 20 photons. What's the wavelength of the laser? How do we tackle the question? So watt, W-A-T-T, is 1 joule per second. So we have 23.6 millijoule per second. We can convert 25 minutes to seconds. It's 25 times 60 seconds. And then we multiply these two numbers together, we get the amount of energy produced by this laser. And that amount of energy should be divided by this many photons. And then we'll get the energy of one photon. Now if you have the energy of one photon, you can calculate its wavelength, because energy is equal to hc over lambda. Therefore the wavelength lambda is hc over energy. So here's the plan. I will first calculate the total amount of energy from this information and then divide it by the number of photons. I will use Wolfram Alpha to do this calculation. This is the information, but really milliwatt. Milli is 10 to the power of negative 3. And 1 watt is 1 joule per second. So I'm going to just write joule per second over here. Joule is the SI unit of energy, second is the SI unit of time, and then multiplied by 25 minutes. Okay, 25 minutes is actually 25 times 60 seconds. So this is the calculation, and this second and this second will cancel. You will get joule in the end. Alright, you will get joule in the end. We will have this amount of energy. Again, this comes from milli. Alright, and then each watt is 1 joule over a second. 25 minutes is 25 times 60 seconds. So we'll get the total amount of energy from the laser. It's going to be 35.4 joule. Now I'm going to divide that amount of energy by the number of photons, 1.15 times 10 to the power of 20. So here you go, this many joules, alright, divided by 1.15 times 10 to the power of 20. Work at the energy per photon. Each photon contains this much energy, 3.078 times 10 to the power of negative 19 joule energy. So this is the amount of energy in each photon. Once we have energy, we can compute the wavelengths. Because energy of the photon is hc over lambda, so lambda is hc over energy. So what I will do is I will use h times c and then divide it by energy. This is the plan. And now h is 6.626 times 10 to the power of negative 34. C is the speed of light. Alright, and then we do this calculation. I'm going to remove the joule and do a numerical calculation here. Alright, work at lambda. Alright, this is lambda. 6.46 times 10 to the power of negative 7. What's the unit? Meters. Why meters? I used SI units for the Planck constant, for the speed of light, for the amount of energy. Therefore, the unit of this number has to be the SI unit of wavelength, which is meter. So this is in meters. Alright, let's look at the question. I think you can just use meters here. You can also convert meters to nanometers. I'm gonna just use meters here. Alright, and I will just copy this 6.46 times 10 to the power of negative 7. Okay, 6.46 times 10 to the, okay, I need to do this, negative 7 meters. If you convert this to nanometers, you just need to multiply this value by 10 to the power of 9, and you will get 646 nanometers. Alright, 646 nanometers is also correct. Let's look at this calculation. Alright, so they did some conversion here, milli, alright, from milliwatt to 1 watt, and 1 watt is actually 1 joule per second. They converted minute to seconds, alright, and they get the total amount of energy on top divided by the number of photons. They get the energy per photon. Each photon contains this much energy. How do we get lambda? Lambda is hc over the photon energy. You plug in the numbers, alright, and I think they did the conversion at the end. They converted 1 meter to a billion nanometers, so you get this many nanometers. Alright, again, it's up to you which unit you want to use. Either way is good. This is good, this is good.